Good morning, guys. Myself Sridhar H, working as an assistant professor in the Department of Electronics and Communication at Government Engineering College, Haveri. Today we are just going to the module 4 of Basic Electronics, that is of 18ELN1424, that is BJT applications, feedback amplifiers and oscillators. Today in this session 6, we are just going to the oscillators. Okay. Oscillators means what? Oscillators are electronic circuits that generate an output signal without the necessity of input signal. It produces a periodic waveform on its output with only the DC supply voltage as a input. That is, it produces a periodic waveform on its output with only the DC supply voltage as a input. That is, the input is the DC voltage. The output voltage can either be sinusoidal or non-sinusoidal depending upon the type of oscillator. That is, it might be having a sine wave, or it might be having the output might be a triangular wave, square wave, or a sawtooth waveform. Different types of oscillators produce various types of outputs including sine waves, square wave, triangle waves, and sawtooth wave. An oscillator is a circuit which produces a continuous repeated alternating waveform without any input. So noise voltage is the one which is acting as the input. Normally the oscillator is not be having any of the inputs. Okay. So this is the basic oscillator concept showing from common type of output waveform: sine wave, square wave, sawtooth wave, and triangle wave. See that. So it is having the oscillator. So just giving it as a DC power input, and we are taking the AC output. So this one is the basic oscillator. This one. So we'll be just getting what all the wave output what we can give in depending upon the input what we people are been giving. That is, it might be getting a sine wave, square wave, sawtooth wave, or a triangular wave. Okay. So there are two major classifications of oscillators: feedback oscillators and relaxation oscillators. Okay. So feedback oscillators, which turns a fraction of the output signal to the input with not phase shift, resulting in a reinforcement of the output signal. See, so you'll be having a feedback oscillator consists of an amplifier for gain and a positive feedback circuit that produces phase shift and provides attenuation. So this one is just a simple block diagram of oscillator with the amplifier here. So input signal Vs, so the output whatever you give the input form that is acting as the input to the amplifier A, and the V0, that V0 is fed back to the network, that is the beta, and the voltage whatever we are getting from this feedback network is the Vf. Okay, so this one is just acting as a mixer signal, so it will just adding with the Vi and Vs as well as the Vf, and we will be getting it as a Vi, and V0 is the output. So this one is the signal from the output is known as the feedback signal, as well as the feedback is the signal from the network, that is feedback network will be acting as a feedback signal to this mixer. Okay. Once the power supply is switched on, the oscillators will be initiated in the system due to electronic noise present in it. So as we are already told that previously, that it will not be having any of the input, so it will be acting on a noise voltage. Okay, next, the noise signal travels around the loop, gets amplified, and converges to a signal frequency sine wave very quickly. The expression of the closed loop gain of the oscillator is gain G is equal to A divided by 1 plus A into beta. A is the amplified voltage gain of the amplifier, and beta is the gain of the feedback network. So if you want, you can just, so A is the amplifier gain and beta is the feedback network. Where, okay, if A beta is greater than 1, so depending upon this feedback signal, whether it is of a greater than, less than, or equal to, depending upon that, we will be getting a undamped, damped, or a normal output. If A beta is greater than 1, then the oscillator will increase its amplitude, while if the gain of the feedback loop is that, then the output will be destroyed. Okay, see, depending upon if A is better than, A beta is greater than 1, then you will be getting this kind of, that is the undamped waveforms. So if A beta is less than 1, then the oscillator will be damped. So that is from increasing from highest 2 points to the 0 point you will be getting. So if A beta is equal to 1, leads to the oscillations which are constant amplitudes here. If see, it is having a constant, that is a normal sine wave what people will be getting, depending upon the frequency and all those steps will be the constant. If the gain of the feedback is unity, then the oscillator will be of constant amplitude, leading to self-sustained oscillatory circuit. Next, once again, the feedback oscillators. Okay, so this one is just the input signal, the same amplifier circuit and the feedback circuit. The output of this is acting as the input to this feedback signal, and this feedback signal output is acting as the input to this amplifier. Okay, see, this the signal is when is the input is small, and this one is the amplified output AF and B. The block diagram of the feedback oscillator is shown in above figure. The oscillator is made from the amplifier and feedback network. The feedback network sends some of the system's output back to be re-amplified after a suitable time delay. Okay. See, the feedback oscillator will be having both amplifier as well as a feedback circuit, and the feedback network sends some of the system's output, that is output, back to the feedback to re-amplify after a suitable time delay. Amplifier has a voltage gain of, that is A of F, and the feedback network has a voltage gain equal to B of F. Of that, or normally we will be telling it as AF and B. So feedback is of two types, negative feedback and positive feedback. So they'll just go through the first negative feedback and later for the positive feedback. Okay, negative feedback, it is also known as degenerate feedback, that is negative feedback or degenerate feedback. In negative feedback, the feedback energy, that is voltage or current, is out of phase with the input signal and thus opposes it. Out of phase means it is the sine wave will be exactly opposite. If it is of a 0 degree, then it will be of a 180 degree or 360 degree. Negative feedback reduces gain of the amplifier. It also reduces distortion, noise and instability. So these are some of the advantage, that is it reduces the gain of the amplifier and also reduces distortion, noise and instability. This feedback increases bandwidth and improves input and output impedance. Due to these advantages, the negative feedback is frequently used in amplifiers. Okay, so due to the advantages, that is of it will increase bandwidth and improve input and as well as the output impedances. So this one is of the circuit is of a negative feedback. See, introduce a feedback of 180 degree phase shift. So Vn is the thing, and the feedback signal what we are getting is of the degree of a 180 degree phase shift, and this one is the simplified, that is the amplified output. See Vin. So this the feedback circuit what we will be getting, it is of a 180 degree out of phase shift with Vin. Okay. Next, so positive or regenerate feedback. In previous slide what we mentioned, negative or degenerate feedback. In this, positive or regenerate feedback. In positive feedback, the feedback energy, that is in the that is voltage or current, is in phase with the input signal and thus aids its positive feed, increases gain of the amplifier and also increases distortion, noise and instability. There it was in negative feedback, it was decreasing, and here it is increasing gain of the amplifier, distortion, noise and instability. Because of these disadvantages, positive feedback is seldom employed in amplifiers, but the positive feedback used in oscillators. See here. So this one is the Vin in phase. Whatever the input, whatever you get in, that will be just sent back to the feedback network, and this one is the amplified output. So they will not be having any of the phase shift. Okay. So normally in the feedback signal you should be having of a 180 degree phase shift, but in this positive feedback you will not be having any phase shift. So the VAF will be in a phase with the Vn. Okay, in the previous figure, that is the gain of the amplifier is represented as A. So the gain amplifier is being represented, sometimes in the previous slide it was being represented as A of F, now it is being represented as A. The gain of the amplifier is the ratio of the output voltage V0 to the input voltage Vi, that is V0 by Vi. The feedback network extracts a voltage Vf. The gain of the amplifier is the ratio of the output voltage, that is V0 by Vi, and the feedback network extracts the voltage Vf is equal to beta into V0 from the voltage V0 of the amplifier. Okay, that is been clearly discussed in the previous slide. And this voltage is subtracted from negative feedback from the signal voltage Vs. Now Vi is equal to what? Vs plus Vf. So Vi is equal to Vs plus Vf here. Vi, that is, okay, wait one sec. See, Vi is equal to what? Vs plus Vf. Okay, so this one. So what is this Vf? Vf is equal to what? Beta into V now. The same thing it has been clearly mentioned. Okay, Vi is equal to what? Vs plus Vf, but Vf is equal to what? Beta into V naught. The quantity beta is equal to Vf by V naught is called the feedback ratio of the feedback fraction. Okay, and now the output V naught must be equal to the input voltage, that is Vs plus beta into V naught, that is multiplied by the gain A of the amplifier, hence Vs plus beta. So we are just substituting the values. So what all that V into V is equal to V naught A Vs plus A into, if we just multiply this, we will be getting into V naught, and if we just remove the A Vs is equal to what? V naught as common, then 1 minus A beta. So what is the what? V naught by Vs is equal to A into 1 minus A beta. So the formula, the gain of the amplifier with feedback is given by AF is equal to A divided by 1 minus A beta. So this one is the standard formula for the amplifier gain, that is AF is equal to A divided by 1 minus A into beta. Okay, so these are the comparison between the positive feedback as well as the negative feedback. So negative feedback energy is out of phase with the input signal, as already know that. So they will be having a 180-degree phase shift. So but in positive feedback, so feedback energy is in a phase with the input, so there will be no phase shift. So it will be having whatever the phase, this is directly the same thing. So here negative in feedback, gain of the amplifier decreases, but in positive feedback, gain of the amplifier increases. Next, in negative feedback, gain stability increases, but in positive feedback, gain stability decreases. Noise and distortion decreases, noise and distortion increases. Increases the bandwidth used in amplifiers and decreases the bandwidth used in amplifier. So normally most of the times we will be just going for the negative feedback due to its advantages. Okay, so AF is the expression, if AF is equal to what? Closed loop gain, A is open loop gain. If there is no feedback circuit, then it will be known as a open loop gain, and if there is a feedback circuit, then it is known as a closed loop gain. So A into beta is equal to what? Loop gain. If A into beta is greater than 0, then it is known as a negative feedback. If A into beta is less than 0, then it is known as a positive feedback. The formula for this one xi is x minus beta into x naught. X naught is equal to what? A into xs minus beta into x naught. The formula for AF what we will be getting is x naught by x, that is A divided by 1 plus A beta. So this is the formula that is same as the previously what it has been did. AF is equal to A divided by 1 minus A beta, and here it will be what? A divided by 1 plus A into beta. Okay, so now we'll just go through some of the problems. Okay, first positive feedback. Let A is equal to minus 10, that is the gain is minus 10, beta is equal to what? The feedback gain is 0.099, and AF is equal to minus 104. Okay, let A is equal to means calculation, directly it will be having a calculation. A into F is equal to what? 10 into, and that A is equal to minus 9.9 and beta is equal to 0.99, and AF is equal to what? Minus 901. So 1% of A causes 91% of change of the feedback, amplitude feedback. So in the negative feedback, the formula is what? Let A is equal to 104, that is whatever the A what you have got, and beta is equal to what? 0.01. A feedback is equal to 100. So that is the 10% change of A causes 1% change of AF. Conclusion: positive feedback increases the gain, but the gain is unstable, and in construct negative feedback decreases the gain, and that is A into beta. If we just multiply, we will be getting this, and decreases the gain and stabilizes it. Okay, see here. Next, second problem, that is a simple one for just we putting the A into beta value. An amplifier A has A is equal to 105 plus or minus 10%. Suppose that we want a feedback amplifier with AF that varies, that is the feedback amplitude varies by no more than plus or minus 1%. Due to variations in A, what is the maximum value of nominal gain AF allowed? And the second part, what we should be calculating, repeat AF if it is allowed to vary both only plus or minus 0.1%. Okay, so the formula for this is what? DAF divided by AF. So DA by A, if you just divided by 1 divided by 1 plus A beta. So this one is the formula. So DA by A is equal to what? 10%, and it is value will be what? 0.1. So 10 divided by 100 if you want, then it will be 1 by 10, that is 0.1. So DAF is equal to what? 1%, that is 0.0F. 0.01. So if you just put the values here, what will be getting is 0.1 is equal to 0.01, 1 divided by 1 plus A into beta. So 1 plus A beta is equal to what will be getting, it is 10. Since A is equal to 10 raised to 5, that is the maximum gain variation is less than 1%. Okay, and next, so dA by, so if you repeat it, then dA by A is equal to 10%, that is same 0.1, and dA by A is equal to 0.001. Then 0.1 if you just calculate, then it will be having a value of 10 raised to 3. Okay, next, the important factor of this oscillator is the Barkhausen criteria. Barkhausen criteria. In electronics, the Barkhausen stability condition is a mathematical condition to determine when a linear electronic circuit will oscillate, and it is widely used in design of electronic oscillators and also in the design of general negative feedback circuits such as op-amps to prevent them from oscillating. So why it is used is to prevent them from the oscillating, that is the feedback circuit such as op-amp. The condition, that is A into beta is equal to 1, is known as the Barkhausen criteria. It implies magnitude of the loop gain, that is A into beta is equal to 1, and phase shift for the loop will be 0 degree or 360 degrees. The main thing what you should be remembering in the Barkhausen criteria is, so always A into beta is equal to 1, and there will be a phase shift of 0% or 360 degree. And the frequency of the noise is the amplifier for which the criteria is satisfied is the frequency of oscillations. By applying this criteria, we can even find the values of transistor parameters like gain required for settling in oscillations. Okay, so this one is a simple Barkhausen criteria for oscillation formula. That is the same thing what we have been oscillator frequency, that is X of in A is the amplifier and beta is the feedback circuit, and X out is the thing, and the feedback beta is the return back to this amplified. So A FB is equal to what? A divided by 1 plus A beta, and A into beta is known as the term loop gain. The formula for this Barkhausen criteria is also what? A divided by 1 plus A beta, that is the amplitude of the feedback circuit. Okay, a feedback amplifier will have sustained oscillation if A into beta is equal to minus 1. Okay, next, Barkhausen criteria is often given different waves by different authors. There are no trivial substitute differences is how it is represented, and not all are correct. Some make comments about shape of waveforms of a sinusoidal, and some add comments that it must have A into beta is equal to minus 1 at only one frequency. Okay, normally Barkhausen criteria will be what? A into B is equal to 1, and it will be producing always a normally of a sinusoidal wave. Barkhausen states that when an oscillator oscillates with steady state signals, then the total phase shift around the loop from input to output and back to input is an integral multiple of 360 degree, and loop gain equal to 1. Okay, so this one is the simple Barkhausen formula, that is amplifier A X naught AF into, that is feedback into X of X. X of S is the input signal, and X of F is the feedback signal. So it is a summation what we will be getting in the mixer will be what? X naught is equal to AF into XS. In real oscillator there is no input signal X of X at all. Okay, as we already know that, so the oscillators will be working with the what? Only with the noise voltage, not it is, the oscillator will not be having any of the inputs, that is of only having a noise voltage. Here it is included to explain the principle of operations. Just for the theoretical explanation, the X of X is being just taken. The oscillator operates under positive feedback, hence the feedback signal X of is summed into the inputs, and the closed loop gain is given by the formula what? That is AF is equal to AS divided by 1 minus AS into B, that is A divided by 1 minus A into B. X is just the formula. The normal formula for the loop gain is what? A divided by 1 minus A into beta, but it is of X of X they are just taken, so we are just taking for the closed loop gain. And the open loop gain formula is what? L of S is equal to what? AS into beta Yes, so this is the explanation for your oscillations. Okay, thank you.